So our second speaker will be Yan. Yan is now a fifth-year PhD candidate in University of Michigan. He actually got the Requiem pre-doctoral fellow. So I know that's a very hard, very difficult, very prestigious award. And then someone get that will definitely be a future star because I got it in my PhD as well. Anyway, that's a joke. And then Yan's research protect the security and privacy of the sensing in several physical systems, and he's currently looking for actually tenure-track assistant professor positions. And today he's going to tell us how you can actually take a picture using EM signal, even in the next door of the room, right? So, which is very amazing. Yeah, takes the stage.
Thank you for the introduction, Dr. Chen. And I'm very excited to share my research with you here. So as shown in the title, I will be explaining the eavesdropping risks against cameras. And we know that today camera sensors are widely embedded into various types of commercial electronics. And it's also interesting that even if we don't directly purchase these camera devices, there are people on YouTube, for example, teaching us how to build IoT cameras using Raspberry Pi camera modules, which I believe many of you here may have tried or just want to try for fun. However, we are computer security researchers, and of course, we also are concerned about the security of our camera data. So software vulnerabilities and misconfigurations are probably the first thing that comes to our mind. For example, it's an old story that IP cameras use default or very weak passwords, which allow adversaries to directly hijack the camera and get the confidential camera data. And as security researchers, we surely know how to fix these problems by setting strong passwords or making software patches. But the new question here we are asking in this work is, assuming all the software and network components of the camera system are secured, how can the camera data still be leaked to adversaries? For example, in the worst case scenario, what if it's an air-gapped camera system that records and stores data completely locally? And our research shows that there are still ways for this kind of leakage in these cases, and the answer lies in the unexplored domain of hardware vulnerabilities of our camera sensors. So here's the threat model. The adversary we investigate in this work is in the form of an external eavesdropper who can set up a physical eavesdropping device equipment in the vicinity of the camera system. And the eavesdropping device uses a radio frequency antenna to pick up the electromagnetic leakage, the unintentional leakage from the target camera systems, and then try to reconstruct the confidential camera videos just by analyzing the unintentional leakage in the environments. So here's what the eavesdropping attack looks like. So for example, a victim has a camera in his room, and he believes that the camera data is only available to himself, assuming all the software access are secured. However, the adversary can actually set up a physical eavesdropping device here, just outside of his room, with an antenna and software-defined radio, and then try to reconstruct the room images in real time. So how can the adversary achieve this, actually? Let's look at the abstraction of this problem. Here we have a ground truth image taken by the camera, and then the adversary tries to reconstruct the image from the electromagnetic signals in the environment. And the reconstruction process, denoted by the function R, represents the eavesdropping device and also the algorithms used by the adversaries. So clearly, as you can see, the key task here, if you would like to get this function R, is to understand how the ground truth image is transformed into the electromagnetic signal. And this is equivalent to understanding which component of the camera system actually generates such kind of unintentional leakage. And this is not an easy task, but through many experiments, we have identified the main source of the leakage to be the standard image data transmission interface in these camera devices. And specifically, we observed there's a strong trend for embedded cameras to use the same standard data transmission interface to connect their camera sensors and the downstream processors, such as GPU, to send their data. So someone might be wondering why these cameras use such kind of standard data image transmission interface. Now imagine you are the CEO of a company that manufactures cars, and you would like to provide some kind of new dash cams, like built-in cameras, to your customers. And of course, you are not going to manufacture the camera sensors by yourself. So what you do is actually to get some camera sensors from companies like Sony and Samsung, and then try to connect these sensors to the processors of your boards. And this is where such kind of interface comes into play. But the bad news here is that such standard data transmission interface is actually transmitting data in a completely unprotected manner. For example, to transmit a video, which can be represented as an array of 2D matrices, the sensor would transmit the data frame by frame, row by row, and then column by column. And this is to say, if that someone can somehow eavesdrop on the transmitted data, they could then at least partially reconstruct the images captured by the camera. And in this specific task I just demonstrated, the adversary eavesdropped on the transmitted data by receiving and analyzing the unintentional electromagnetic leakage from the camera circuits distributed in the ambient environment. And the camera data interface transmits, so basically the interface transmits raw image data encoded in digital bits according to the specific interface protocol. But the digital bits transmitted over the cables are actually achieved by physical alternating currents and voltages over the cables and in the transmission circuits. So everybody knows Maxwell's equations. When there are alternating currents and voltages, there will be an electromagnetic field around these sensors. However, the transmission cable of the camera sensors are actually acting as unintentional antennas that are unwittingly broadcasting the plain image data to the adversaries over the air. So this figure on the right is showing a very simple example where a camera is capturing a black and white image, and we're also showing the electromagnetic signals received by the antenna when the camera is transmitting the data of a specific row in the image. And you can clearly see how the brightness of the image correlates with the amplitude of the electromagnetic signal in the ambient environment. All right, so with this information, I think we can now start putting this together. We can do this kind of correlation frame by frame, row by row, one by one, and then we can get a complete image. And the next question is how similar the reconstructions can be to the original image. And our experiments do show there are many interesting and unavoidable distortions in the reconstructions. So for example, a very interesting phenomenon we observed is that when we moved the antenna around the camera in the space, we actually see varying degrees of amplitude of the reconstruction image. And in some cases, we can even observe a completely inverted polarity of the original image. And again, through many experiments of hypothesis testing, we found that the cause is the multi-wire structure of this transmission interface. So basically, these interfaces have both clock lines and also data lines, and they could even have multiple data lines according to the specific transmission protocol. So imagine if you only get the signals from the data from the clock line, it's relatively a stable signal, so that you will get this kind of white, completely white image. But if you only get signals from the data line, you can reconstruct a relatively similar image from to the ground truth. However, when your antenna is at certain positions, you're actually picking up the mixture of the signals from the two wires, and they can actually cancel each other out. And this is how you're getting this kind of inverted polarity in your reconstructions. And besides the distortions caused by the position of the antenna, another major type of distortion is caused by the fact that most of the time, a practical adversary can only get a signal bandwidth on the order of 10 megahertz. And this means that they cannot get the accurate information of each individual bits transmitted over the cables. But instead, they are just getting a statistical summary of the transmitted bits. And this caused a line of very interesting distortions here. For example, it's only feasible for adversaries to reconstruct a grayscale image so that like all the colors are lost. And even the grayscales in the reconstructions are completely different from the original grayscales in the ground truth image. And meanwhile, you can also observe a lot of high frequency noise and some additional light gradient patterns in the reconstructions that are not observed in the original image. And finally, you get a little bit different information and different images at different frequency bands. So taking into consideration all these phenomena, we could finally arrive at a model that explains this whole camera leakage process. And this model shows that despite some kind of variations in this process, there should still be some invariant structures or transformations in the distortions. And this suggests that it might be possible to build an algorithm to map the noisy reconstruction back to the original image domain. And following this kind of analysis and hypothesis, we were able to build a signal processing pipeline that combines information from multiple electromagnetic frequency bands and then uses an image-to-image translation network to get a high-quality image. But of course, as you can see, we're using a translation network, and it requires a training process, so there will be problems of generalizability. So due to the time limit, I cannot elaborate on that, but I refer you to our paper to find more details on how generalizable this kind of eavesdropping approach is over different types of camera devices and also different environmental factors. All right, finally, here are some interesting evaluation results. Overall, we tested 12 commercial devices that have embedded cameras. And of course, home cameras might be the first thing that we think about. We found that this category of cameras are actually generating very strong leakage signals that would allow adversaries to reconstruct images from several meters away, even through walls and doors in many cases. It's also worth noting that besides the dedicated IoT cameras, the cameras we tested also include other things like the smart screen devices manufactured by Baidu, and also some USB cameras, and also even spy cameras that completely records and stores data locally. And besides home cameras, which could be the main target, we found that dash cams are also having very strong leakage and allows you to eavesdrop on from several meters away. For example, many dash cams today are having this kind of inward-facing camera units, which record the interior of the car while you are driving or when you park. So using this kind of eavesdropping technique, this actually could allow adversaries to peek through, tell which people or how many people are in the car without directly peeking through the window. And not surprisingly, we found that smartphone cameras also leak. But the good news for users is that with our current eavesdropping setup, the eavesdropping distances against the smartphones is relatively small, often on the order of several centimeters. So like the largest distance we could get is about 30 centimeters with a Google Pixel phone. It is not impossible to eavesdrop at such kind of short distance, but the adversary does need to be more creative. For example, by disguising the eavesdropping device as a malicious rental power bank, which can get really close to the cameras. And now I believe that many people are wondering, what are the factors affecting this kind of eavesdropping distance? Because if we understand these factors, we can potentially actively control them as a mitigation or a solution. And some of you might already thought about the physical factor of the cable length. And so because the data transmission interface are acting as an unintentional antenna, we found that generally the longer the cable is, the stronger the leakage will be because it has higher efficiency for the electromagnetic leakage at 100 megahertz or even 1 gigahertz, that range. And our observation is that home cameras and dash cams often use very long cables, as I'm showing here, often to support some interesting form factors like tunable camera angles that will require their camera sensors to be placed pretty far away from their processor boards. So you need to connect them with a relatively long cable. And a relevant factor is the shielding material of the cable, of course. And again, we found home cameras and dash cams often do not apply any kind of shielding to their cables, which is a sad story. And luckily, we found that smartphone cameras often have the shortest cable and also the best shielding material, contributing to the relatively short eavesdropping distance. And of course, coming back to the original problem, I hope I have convinced you that it's a really bad idea to kind of DIY this kind of home security cameras on your own. And besides the physical and hardware factors, we found there are also potential improvements for software or firmware. As I mentioned, this kind of leakage is generated by the image-specific bit flips on the transmission cables, right? So we found that actually the interface designers can potentially improve their design by simply rearranging the bits they transmit. For example, by placing the same bits of adjacent pixels that would have similar values together, you can actually smooth out many unnecessary bit transitions and thus greatly reduce the electromagnetic leakage in the environment. Okay, finally, want to give some discussions about potential future research. As I have shown, eavesdropping distance is probably the best, one of the main focuses. And so our current setup is using a relatively commercial, I would say, cheap setup. For example, like an antenna, like $15 you can get on Amazon. And with this setup, we could get smartphone camera signals from about 50 centimeters away at most. I do want to point out there exists previous research that investigated using lab-customized kind of antennas to receive the smartphone camera signals, and they could do like 5 meters away. So I believe it's a really interesting future research direction to further explore the design space of this kind of eavesdropping receiver device. And here, the protocol I talked about is transmitting completely plain data. However, there do exist some cameras, like not embedded cameras, for example, standalone USB cameras. We found that they are actually transmitting encoded data, for example, H.264 compression, right? But the bad news is that they're still leaking information. And even if you cannot directly reconstruct the image using our existing technique, because it requires you to get a very accurate parameter of the transmission protocol, but still, you can use some simple machine learning algorithm to figure out, what the scene is in the camera by analyzing its like spectral features. Very simple. And finally, I just want to mention that this vulnerability is part of the big picture of my research in the security and privacy of sensing systems. And besides information leakage, we also investigate how such characteristics of sensors also allow adversaries to inject false information back into the systems or to be utilized by system defenders as for some good purposes, such as enhancing the security of our existing systems using multi-model sensing. As Dr. Chen mentioned, I'm also currently on the job market, so if you would like to talk to me, I'm more than happy to chat in the hallway. And so that concludes my talk. Don't forget to take a photo of this QR code so you can access the demo and also the open source codes for replication. And I'm happy to take any questions you may have. Thank you.
Questions?
Yeah, and great talk. So can you go back to the result, the distance result?
Yep.
So it seems that Chinese products have a longer distance, meaning that probably because of the EMI, EMC requirements of the Chinese product, it's much weaker than the Korea and the US.
I couldn't hear.
EMI, EMC compliant
Yeah.
requirements of the Korea
yeah.
and the US is much stronger than the one in China.
That's possible. That's possible. We didn't. That's a great point that we didn't really get to consider, but I think it's worth digging it up to compare it. And also, I want to mention that this standard data transmission interface, they specify that we have very strong electromagnetic compatibility designs in our protocol, but turns out they don't. So it's sometimes the protocol is one thing, and the actual hardware design is kind of another thing, and also the regulation, how strong the regulation is.
Because what I've heard is that in case of Samsung, they have done, tons of experiments so that because people care about their health.
Yes.
Because of the EM emanations.
Definitely, yeah. Thank you.
Thanks. That was fantastic talk. Nader Sabash, UCLA. So for these cameras, so I noticed that it was around 200 megahertz, the kind of the leakage range. Was it the same for all the cameras, or was it significantly changing?
It's a very wide range. I would say it will start about 100 megahertz or even 50 megahertz, and you will get these harmonics because they are transmitting bits as square waves, right? You get harmonics. And we found that different cameras have different best frequencies because of the different layouts and the cable length. You also get gigahertz frequency. And we also found that in long distances, probably higher frequencies works the best. That's our experience. Yeah.
And then was it always harmonics of the clock, or that number just meaningful, or was it just random?
It's mostly the harmonics of the clock frequency because the data is transmitted. I think is the data rate is twice of the clock frequency. They're doing overclocking in the protocol. Yeah.
Thank you.
Hi. So let's say I'm an attacker and I want to put one of these close to your camera so that I can get the image. Do I have to do some special tuning or pick the right attack box in order to get the image, or will it work with any generic camera?
Different cameras definitely require you to tune the parameters a little bit. But like in the code we're providing, so basically we're using an existing software, we customize it. But basically you can use a GUI to tune the parameters relatively simply, I would say. A major challenge is actually, so for example, if I'm a researcher, I want to do future research to automatically investigate this vulnerability, a key challenge is how to sweep through a set of different parameters and also determine where there is really a reconstructed image. So it takes some effort, definitely takes some effort. I would say like it takes us like about 30 to like 1 hour to profile one single camera device. That's why we didn't do many here.
Thanks. And also, could I stick a device that broadcasts in the same frequencies in order to implicate somebody who has a camera but isn't doing something? So I basically broadcast something that they wouldn't want their camera to pick up.
I think I didn't quite get the question. Do you mind repeating that?
So the idea is to do an implication attack where you have the camera, but I want to replace or overwrite what your camera is unintentionally broadcasting with a stronger signal, so that my fake signal will be received by somebody. Like, let's say you had somebody monitoring a camera for a legal thing. The idea is to effectively replace your signal, or
Got it.
overwhelm your signal.
Got it. So like it's more like a jamming, kind of protection.
Yeah, jamming plus.
Yeah. I think it's actually, if we're looking at an external protector that is like emitting some jamming signal or replacement signal, it's actually very difficult because the signal is basically everywhere. It's a baseband signal. It's not a carrier signal very focused on a specific frequency. So like the signal is like spanning a very large frequency band. So imagine you need a jamming device that wants to emit some signals. The jamming device has to be very expensive to cover such a large frequency band. Yeah.
Okay, thanks.
Okay, so let's thank the speaker again.